Good afternoon, students.
Good afternoon.
Good afternoon, all of you. So let us start the discussion without wasting any time. So last class we have seen the concepts of adsorption, like differences between physisorption, chemisorption, all that points we have seen. Now in today's session we'll be looking at different factors. In the factors also we have seen the nature of adsorbent, nature of adsorbate, effect of temperature. These factors we have studied. Now the next is effect of pressure. If you go with the effect of pressure, what happens if it's a gaseous reaction, or you can say the gaseous species are there above the adsorbent. If I apply more pressure from the top, obviously because of more pressure, more is the extent of adsorption. If I try to apply pressure, more is the pressure, more is the extent of adsorption. And with this effect of pressure, we have two isotherms like Freundlich adsorption isotherm and Langmuir adsorption isotherm. The adsorption isotherm, there are been two types, as I was saying, Freundlich adsorption isotherm and Langmuir adsorption isotherm. The extent of adsorption of a gas on a solid is generally expressed as x by m. What is x, students, here? The extent of adsorption of a gas on a solid is generally expressed as x by m. X is the mass of adsorbate, m is the mass of adsorbent. X by m is the mass of adsorbate per unit mass of adsorbent. Mass of adsorbate per unit mass of adsorbent, that is nothing but your x by m. And x by m is equals to k into p power 1 by n. X by m is equals to k into p power 1 by n, where k and n are constants. X is the mass of adsorbate, m is the mass of adsorbent, p is the pressure. Theoretically, x by m is directly proportional to pressure. Theoretically, x by m is directly proportional to pressure. So x by m, if you take on the y-axis, pressure if you take on the x-axis, what type of curve you are going to get?
Straight line.
Straight line, p power 1 by n.
No, sir.
Okay, x by m is equals to k into p power 1 by n. You will be getting a curve like this. And you can observe the same curve at the three different conditions, like at very low pressures, at moderate pressures, and at very high pressures. At very low pressures, it looks like a straight line. At moderate pressures, you will have the curve like any curve. And at very high pressures, you will be having like independent of pressure. So x by m is directly proportional to pressure. At a very low pressure, it will be looking like a straight line. This is a straight line, low pressure. Moderate pressure, x by m directly proportional to p power 1 by n. And high pressures, independent of pressure. So theoretically, x by m is directly proportional to pressure, theoretically. Because more is the pressure, more should be the adsorption happening on the surface of the adsorbent. Right? Physical adsorption, if you try to plot x by m versus pressure at three different temperatures, T1, T2, and T3, what is the relationship between T1, T2, T3?
T1 greater than T2 and T3.
Because at a high temperature, like if you consider any pressure, at this particular pressure, what is the extent of adsorption? If I try to draw a straight line parallel to y-axis at a particular pressure, so these are the respective joints. That means this is the extent of adsorption at a pressure P at T1 temperature. This is the extent of adsorption at a pressure P for T2 temperature. This is the extent of adsorption at a pressure P for T3 temperature, where the extent of adsorption is higher. Extent of adsorption is greater, then temperature is lower. Okay, low temperature means more extent of adsorption, more extent of adsorption. When the temperature is low, the extent of adsorption will be high. So or I can also say extent of adsorption is low when the temperature is high. So at high temperature, like which extent of adsorption is low? So at the T1 temperature, so T1 should be highest temperature, T1 greater than T2, T2 greater than T3. This was the relationship between T1, T2, T3, where you have plotted x by m versus pressure, right? Types of adsorption as them. As I was saying, Freundlich adsorption as them. Physical adsorption can be mainly explained by Freundlich adsorption as them. Langmuir adsorption as them will be explaining mainly chemical adsorption or chemisorption. We'll discuss these two types. Freundlich adsorption as them or physical adsorption. Freundlich adsorption as them is obeyed by the absorption where the adsorption forms single layer on the surface of adsorbent. Again, you read the statement. Freundlich adsorption as them is obeyed by the adsorption where adsorbate forms single layer. But we know that physical adsorption can be multi-layered. Physical adsorption can be multi-layered at high pressures. At a very high pressure, like I have told you, like wall is there and I am applying pressure and hitting the wall. So multi-layer can be formed. Physical adsorption can be forming multi-layer at high pressures. Freundlich adsorption as them is obeyed by the adsorption where the adsorbate forms single layer. Whenever the adsorption is single layer, then you can follow this Freundlich adsorption as them. Freundlich adsorption as them equation will be x by m is equals to k into p power 1 by n. According to Freundlich adsorption as them, x by m is equals to k into p power 1 by n, where n should be greater than or equal to 1. In general, 1 by n lies between 0.1 to 0.5. The value of 1 by n will be lying between 0.1 to 0.5. And x by m is equals to k into p power 1 by n. This was the Freundlich adsorption isotherm equation. This equation has been given by looking at the plot of x by m versus pressure. We have drawn the graph. So no mathematical equation is given first and then the graph has been plotted. That is not the way you have to study the physical sequences or the physical phenomena, whatever it is happening in nature. They were observed experimentally. There, whatever the observations we have made, we have plotted in the form of a graph. From the graph, we try to develop the mathematical equation. That is how the mathematical equation can be obtained. But nowadays, what we are doing, we know the equation. From that equation, we are trying to plot a graph. But the reality is different. In the real life, what we are doing is we are doing the experiment. We are getting the data. That data you are plotting in the graph paper. You are plotting a graph. And now for that particular graph, you are studying, you are understanding what is the curve looks like, what was the mathematical equation. Okay. So in general, 1 by n value is in 0.1 to 0.5. X by m represents the mass of gas adsorbed on unit mass of adsorbent. K and n are constants at a particular temperature and a particular adsorbent and adsorbates. K and n values, K value and n value are constant at a particular temperature and a particular adsorbent and adsorbates. Like K and n value depends upon nature of adsorbent and adsorbate at a particular temperature. So K and n depends upon temperature, also depending upon adsorbate and adsorbents. Is that clear?
Yes.
Yes, right. Very good. Yeah, look at the three regions. X by m, like three different colors has been given. X by m is directly proportional to pressure whenever the pressure has been maintained low. That is, it is looking like a straight line. At low pressure, at moderate pressure, and at very high pressure, three regions you can consider. At low pressures, what you can have x by m directly proportional to pressure. The same curve I have written for the adsorption in solution. What you have written? Adsorption in solution. The same type of equations you can follow, and x by m should be directly proportional to concentration. See, you can write or not. At a moderate pressure, x by m is directly proportional to p power 1 by n. Same you can understand. At a moderate pressure, for adsorption in solution, x by m is directly proportional to c power 1 by n. At high pressure, x by m is directly proportional to p power 0. At high pressure, what you can write? X by m is directly proportional to c power 0. That means at a very high pressure or at very high concentration, what you can say? Since already all the surface has been adsorbed, it doesn't matter how much pressure you apply or it doesn't matter how much concentration is there. Since already adsorption has been covered, like all the surface has been adsorbed, it doesn't matter how much concentration or pressure we are applying, further adsorption will not occur because there is no surface for the molecules to go and get stick. Okay.
Yes.
In logarithmic form, how you can write the same expression? X by m is equals to k into p power 1 by n. So logarithm of x by m is equals to logarithm of k into p power 1 by n. So logarithm of x by m is equals to log k plus 1 by n log p. Logarithm of x by m is equals to log k plus 1 by n log p. This was the expression. And you can similarly try to plot a graph taking logarithm of x by m on the y-axis, log p on the x-axis. If you try to plot a graph, you will get a straight line and with a slope of, what is the slope now?
1 by n.
Slope is equals to tan theta, and we know the value of n is positive. So 1 by n is also positive. So theta will be belonging to quadrant 1, and you can have intercept of log k. Okay. The same you can study. In the logarithmic form, you can try to write the equation and try to understand what was the intercept and as well as what was the slope.
So,
Yes, please.
what does this 1 by n tell us? Like, what does it mean?
Like whatever the curve you have, right? Whatever the curve you are getting raw.
Yes, sir.
This curve equation, that is x by m is proportional to p power 1 by n. That means it is y directly proportional to x power 1 by n. N is some constant. Like you can take the value of n. 1 by n is lying between 0 to 1. That means 1 by n, let us take as 1 by 0.5. Can I take 1 by n as 0.5?
No, sir.
1 by n can I take as 0.0 to 1? In between 0 to 1, we have 0.5 or not?
Yes, sir. Okay.
Yes or no? So I can take 1 by s as 0.5. So y directly proportional to x power 0.5 or y is equal to some constant k into x power 0.5. This was the equation for that particular curve. Or you can say y square is equals to k into x. Y square is equals to 4ax is a parabola. That means whatever the 1 by n they are trying to write, they try to explain the equation of this particular curve. Here I have taken 0.5 for your simple understanding. You can write it as a parabola, y square equal to 4x. But you can have x power 0.6 also, which is not exactly parabola. Yes or no?
Yes, sir.
So that 1 by n value is actually trying to represent the equation of this particular curve. Up until here we have a straight line. After that it is looking like some curve. The equation of that curve we have to try to write down in terms of mathematical. It has been given as y directly proportional to y is x by m, directly proportional to x is pressure. So p power 1 by n, and 1 by n value can be lying between 0 to 1. So it can be, if you take it is 0.5, then it is looking like parabola.
Yes, sir. Understood.
Yes. Drawbacks of Freundlich adsorptionism. Can you think of any drawback? It explains physical adsorption up to moderate pressure, but fails at high pressure. At high pressure, can it explain the physical adsorption? No. Because as per Freundlich adsorptionism, x by m is directly proportional to p power 1 by n. So as the pressure is increasing, x by n should increase. But at high pressures, it is not the adsorption is not going to be depending upon the pressure. So at high pressure, complete adsorption, the adsorption has been stopped because already surface has been occupied. So physical adsorption can be explained up to moderate pressures, but at high pressures, it is failed to explain. And any other point you can think of?
At high
Freundlich.
concentration,
Yes, please.
at high concentration also.
At high concentration also we can talk about the same scenario. But these are adsorption mainly for gases because it is coming under the effect of pressure. And Freundlich adsorption never considered surface area into account if you think carefully. Yes or no? Freundlich adsorption never included surface area into the account. Freundlich adsorption do not consider surface area in the discussion of adsorption. But mainly Adsorption is actually based on the surface area, unbalanced forces. So since the surface area itself is not included in this Freundlich adsorptionism, so that was also not accepted greatly. That is also a great drawback, because because of surface area only, we have this adsorption happening. Because of unbalanced force on the surface only, this adsorption is happening. Surface is not at all included in this discussion. So that is why it is also acting as a drawback. Adsorption in solution, like liquid plus solid. If we take adsorption in solution, again we have the same equation, x by m is equals to k into c power 1 by n. X by m is equals to k into c power 1 by n. That is the respect to adsorption happening in solution. Yes or no? In solution also, whatever adsorption occurs, the extent of adsorption happening in solution, that is directly proportional to what? Adsorption. Can I say it is directly proportional to nature of, like, it is directly proportional to concentration, first thing. Concentration of solution. First and basic thing you can understand. And directly proportional to surface area. Surface area of adsorbent, and inversely proportional to temperature. And it is also depending upon adsorbate and adsorbent. Depends upon nature of adsorbents and adsorbates. Adsorption in the solution inversely proportional to temperature, because with increase in temperature the molecular motions increase. With increase in molecular motions, what is going to happen? The adsorbate molecules will not go and stick to the surface. With increase in surface area of the adsorbents, what will happen? With increase in surface area of the adsorbents, more is the surface area, more is the adsorption. With increasing concentration also, more is the adsorption, and this was the ultimate equation. The following observations have been made in the case of adsorption from solution phase. As I was saying, the extent of adsorption decreases with an increase in temperature because molecular motions increase. The extent of adsorption increases with an increase of surface area. With increase in surface area, what happens? The extent of adsorption will be increasing. The extent of adsorption depends on the concentration of solute in the solution. The extent of adsorption depends on the concentration of the solute in the solution. The extent of adsorption depends on the nature of adsorbent and nature of adsorbate. These are the same points which you have explained or not?
Yes.
On all these factors, the adsorption is going to be depending upon. The adsorption will be depending upon all these factors. Example, you can take dye solution in the charcoal. Like for this, what was the relation? X by m is equals to k into c power 1 by n, and you can try to plot a graph between logarithm of x by m, logarithm of x by m, logarithm of x by m. If you try to plot with respect to log c, you will have again the straight line with the slope of log k and with the intercept of log k and slope of 1 by n. Yes. X by m is equal to k into c power 1 by n, where c is the concentration of the solute in the solution. C is the concentration of adsorbate in the solution. The same equation similar to your Freundlich adsorption as them. Same type of graph you will get, log k, slope as 1 by n. The next type of adsorption as them, after your Freundlich adsorption as them and absorption solution, is the Langmuir adsorption as them. Langmuir adsorption isotherm. This Langmuir adsorption is the mainly useful for chemical adsorption, and it has taken surface area into account. Langmuir in 1916 derived a simple adsorption algorithm on theoretical considerations based on kinetic theory of gases. This was named as Langmuir adsorption algorithm. But what was his theory and how he has actually given the formula and how that can be understood, you can understand from the respective postulates. Like according to Langmuir adsorption algorithm, there was two forces. One is the condensation, other is the evaporation. Let us take the postulates now. Postulates, you can say. The first postulate of Langmuir adsorption algorithm is, in the adsorption there are two opposing forces. What are the two opposing forces, or what are the two opposing factors? One is condensation, the other is evaporation. So this is the beaker, like this is a metallic surface and this is the surface of that particular solid. If you consider the rate of condensation, like gas molecules are there above, and here you have the surface points, the gas should come and stick to the surface. The gas should come and stick to the surface. Now can I say the gas molecule should come and stick to the surface? Condensation means what? Condensation means gas molecules coming and getting adsorbed. Evaporation means whatever the molecules which are already adsorbed, they will desorb. The gas molecules have a tendency to come and adsorb. The molecules which are already adsorbed, they can dissolve. These are the two factors, two opposing factors. That means there is some rate of condensation, there is some rate for the evaporation. So rate of condensation is actually happening. The condensation is happening why? Condensation is happening to balance the unbalanced forces. Whatever the molecules already got adsorbed, they also have a tendency to increase their randomness, because of that evaporation occurring. So two opposing forces, condensation is occurring to balance the unbalanced forces. Again, the molecules which have been adsorbed, they may experience electronic repulsions, like molecule adsorbed here at this point and molecule adsorbed here. They may experience electronic repulsions also. They may dissolve also. So at a particular time t, rate of condensation should be is equals to rate of evaporation or not. So there was an establishment of equilibrium in the process of adsorption. There was an establishment of equilibrium in the process of adsorption. Now understand this point. Rate of condensation depends upon what? Condensation means getting adsorbed. I have a particular surface. Like let us say this much, like this is a total surface area, right? I have this much already adsorbed, only this part. Rate of adsorption or rate of condensation depends upon the surface area available for adsorption. Yes or no? Rate of adsorption will be depending upon how much surface area is available for adsorption. Like it depends upon fraction of surface area which is free, so that the adsorption can occur. Also, it depends upon pressure. If I apply more pressure, more is the adsorption. So rate of condensation is depending upon condensation. That will rate of condensation depends upon the uncovered surface of the adsorbent. How much surface is not covered, on that rate of condensation depends upon. Rate of evaporation depends upon the covered surface of the adsorbent. How much, like evaporation should occur means whatever the adsorption already take place, from those points only the molecules will go into the vapor state. Rate of evaporation depends on the covered surface of the adsorbent, whereas rate of condensation depends upon the uncovered surface of the adsorbent. Is that point clear?
Yes.
Yes, right. Rate of condensation also depends upon pressure. Rate of evaporation do not depend upon pressure. Every adsorption, next, that is the first postulate. Like it says, condensation and evaporation both are there, two opposing forces. At the stage of equilibrium, rate of condensation and rate of evaporation, they are going to be equal. Every adsorption site is equivalent, and that the ability of particle to bind there is independent of whether or not nearby sites are occupied. That means if you have 10 sites there, this is one site, site 1, site 2, site 3, site 4, site 5. At this particular site, adsorption should occur. The adsorption will occur at this particular site or not, that is independent of whether the adjacent site is getting adsorbed or not. Every site is independent, like it is equivalent. Every adsorption site is equivalent, and the ability of a particle to bind there is independent of whether the nearby sites are adsorbed or not. Adsorption takes place on the surface of solid only till the whole of surface is completely covered with a unimolecular layer of the adsorbed gas. Like if all the surface points have been occupied, then there is no further adsorption happening. Yes or no? Adsorption takes place on the surface only till all the surface points got adsorbed such that a unimolecular layer has been there. Is that clear?
Yes,
Yes, sir.
As I have told you, an equilibrium will be set up at a stage when the rate of condensation is equals to rate of evaporation. At this stage, there will be an establishment of equilibrium. Adjacent adsorbed molecules do not interact with adsorbed molecules, but adsorbed molecules have equal ability to interact. Understand this point. Adjacent adsorbed molecule, like we have surface points. Here we have some molecule adsorbed. This molecule will not interact with the other molecule, but it has equal ability to interact. It has the ability to interact, but it will not interact. The rate of condensation also depends upon the pressure of the gas. Rate of condensation also depends upon the pressure of the gas. Since according to kinetic theory of gases, number of molecules striking per unit area is directly proportional to pressure. Like if you are talking about adsorption, from the top, if you are applying more pressure, then only more adsorption will occur. Rate of condensation will be depending upon the pressure of the gas as well. Rate of adsorption will be depending upon the pressure of the gas. Like more the pressure, more will be the number of molecules hitting the surface, so more will be the adsorption. And mathematically, the formula can be given as x by m. That is, the extent of adsorption is equals to some constant a into p divided by 1 plus b into p, some constant b into p. Is that clear?
Yes.
Yes or no? But we can actually understand how this equation can be obtained. Like you can take a particular surface. On this particular surface, let us consider, let a theta be the fraction of surface area which adsorbed. Let theta be the fraction of surface area adsorbed. Let a theta be the fraction of surface area adsorbed. So rate of condensation will be what? Rate of condensation will be equal to,
Uncovered surface area.
then it should be proportional to what?
Theta minus A.
Fraction I'm saying, right? Like one is the total surface area then. If theta is a fraction, so 1 is the total surface area. So rate of condensation should be directly proportional to 1 minus theta. And this rate of condensation also depends upon pressure. So 1 minus theta into p. Rate of evaporation is directly proportional to theta. It is not depending upon pressure. Like how many molecules have been adsorbed, like how much surface is already covered. On that only rate of evaporation depends. Rate of evaporation directly proportional to theta. Rate of condensation directly proportional to 1 minus theta. Because theta is a fraction of surface area occupied, 1 minus theta is the fraction of surface area unoccupied. On that unoccupied surface area, whatever the unoccupied surface area is there, that will be directly proportional to rate of condensation and also the pressure. Rate of condensation, rate of evaporation we have written. So rate of condensation, the proportionality, if I try to remove, I can write K1 and also I can write K2 here. At equilibrium, what happens? Rate of condensation is equals to rate of evaporation. That means from here I can write K1 into 1 minus theta into P. That should be equals to K2 into theta. So from here I can eliminate 1 minus theta by theta is equals to K2 by K1P. So I can write down the equation 1 by theta. I can write down the equation 1 by theta minus 1 is equals to K2 by K1P. So 1 by theta I can write as K1P plus K2 divided by K1P. Or from here I can write theta as from here I can write theta as K1P divided by K2 plus K1P. Theta, what is theta? Theta is a fraction of surface area absorbed. Can I say extent of absorption? Extent of absorption, whatever we are talking about, extent of absorption should be directly proportional to fraction of surface area. So extent of absorption is directly proportional to fraction of surface area absorbed. That means x by m should be proportional to theta. So I can write x by m is equals to some constant k3 into theta. What is theta? K1p divided by, I can take a k1 constant again, k1 into, I can take k2 constants. K2 I have to take constant because it is written in the form of 1 plus bp. So k2 constant, if I take k2 into 1 plus k1 by k2p, that means x by m is equals to k1 k3 by k2 into p whole divided by, I can write the ultimate formula here, x by m is equals to k1 k3 by k2p whole divided by 1 plus k1 by k2p. This is nothing but some constant a into p divided by 1 plus some constant b into p, or not?
Yes, sir.
So that is how we can derive this equation. The extent of absorption x by m is equals to some constant a into p divided by 1 plus another constant b into p. So based on this Langmuir adsorption algorithm and the postulates given, you can actually get to this equation. Whereas the same type of equation in the Freundlich adsorption algorithm or from adsorption of solution, adsorption in solution can be written as x by m is equal to k into p power 1 by n, or x by m is equals to k into c power 1 by n. Similarly, the adsorption from the Langmuir, extent of adsorption from the Langmuir adsorption algorithm is given by x by m is equals to ap divided by 1 plus bp, where a and b are constants. Values of a and b are constants, and obviously they depend upon nature of gas, that is adsorbate, nature of solid adsorbents, depends upon temperature, and they are determined from experimental data. A and b are constant, like x by m is equal to k into p power 1 by n. What are k and n? They are constants. Similarly, x by m is equals to ap divided by 1 plus bp. What are a and b? They are constants. They depend upon what? They depend upon the nature of adsorbent, temperature, and they have to be obtained from the experimental data. Like x by m value will calculate different pressures. So whatever the x by m will get at different pressures, we'll write in this equation format, and from that only we try to figure out the values of a and b. Clear?
Sir,
That's right. You don't worry with the derivation part, okay? Derivation you don't need to derive, but I have just given for your better understanding. Like instead of directly giving the formula to remember, if you can derive it, we can try to understand it carefully. Applications of adsorption. Adsorption, if you try to think of the applications, production of high vacuum, humidity control, heterogeneous catalysis, there are different applications. So all those applications we can understand now. Production of high vacuum, how you can just produce the high vacuum. So high vacuum can produce like remaining traces of air, like whatever the traces of air we have, traces of impurities in air, traces of impurities in air can be removed. Traces of impurities in air can be removed by adding activated charcoal. By adding activated charcoal, which will be acting as an adsorbent so that adsorption occurs. Humidity control, you can actually control the humidity, like silica and alumina gels are used as adsorbents. Silica and alumina gel are used as adsorbents. Heterogeneous catalysis. Heterogeneous catalysis means you can think of homogeneous catalysis, heterogeneous catalysis. You have studied, right? Homogeneous catalysis means what? Homogeneous catalysis means reactants and catalysts, they are in the same phase. Heterogeneous catalysis means reactants and catalysts are in a different phase. So reactants will first adsorb on the surface of the catalyst, then only the adsorption will, then only the rate of reaction can be increased. Reactants gets adsorbed on the surface of catalyst. Reactants get adsorbed on the surface of catalyst, and thereby reactants and catalyst, they are in a different phase. So that is nothing but homogeneous catalysis. In curing diseases, the diseases can also be cured. Different kinds of diseases can also be cured with respect to this adsorption, like whatever the drugs we have, like we have seen about drug target interaction. The drugs will actually, there are number of drugs where the bacteria will be going and getting adsorbed in the drug. Since the bacteria will be adsorbed in the drug, that will be killed. The bacteria or virus can get adsorbed on the drug, and thus it gets killed. Froth flotation process, it is actually a way to concentrate sulfide ores. It is a way to concentrate sulfide ores. Gas masks, like inside the, like wherever you are wearing the gas mask, layer will be having poisonous gases. Inside gas mask, inside gas masks adsorb like poisonous gases. Poisonous gases can be adsorbed so that you cannot breathe them. Removal of coloring matter from solution. The colored substance can also be adsorbed. The colored substance can be adsorbed. So these are the different applications. These are the different applications of adsorption. Is that clear, students?
Yes, sir.
Adsorption, absorption, occlusion, sorption, desorption, definitions, physical adsorption, chemical adsorption, differences, thermodynamics of adsorption, delta H, delta S total, delta G, and effect factors affecting nature of adsorbents, nature of adsorbates, temperature and pressure. With respect to pressure, we have seen Freundlich adsorption algorithm, Langmuir adsorption algorithm, and also for solution x by m is equals to k into c power 1 by n. And then finally we have seen the applications of adsorption. So then let us try to solve some numericals on adsorptions. Try to solve this. The graph between logarithm of x by m versus log p is a straight line inclined at an angle of 45 degrees with intercept of 0.6. So this was a graph. So we know x by m is equals to k into p power 1 by n. Logarithm of x by m is equals to log k plus 1 by n log p. Logarithm of x by m is equals to log k plus 1 by n log p. So logarithm of x by m you can take on the y-axis. Log p you can take on the x-axis. So you have a straight line which is inclined at an angle of 45 degrees. So and intercept is log k actually. So what is the slope? Slope is equals to 1 by n, that is equals to tan theta, tan 45 degrees. What is tan 45?
One.
Tan 45 is 1. So 1 by n is equals to 1. And intercept is 0.60. What is intercept? Log k. Log k is equals to 0.6. So k is equals to what? 10 power 0.6. And they are asking what will be the extent of adsorption at a pressure of 0.3 atmosphere. X by m is equals to k into p power 1 by n. So x by m at a 0.3 atmosphere, at a 0.3 atmosphere is equals to k value 10 power 0.6 into p 0.3 whole power 1 by n. 1 by n is how much? 1 by n is 1. So x by m at a 3 atmosphere, at a 0.3 atmosphere is equals to 3 into 10 power minus 1 into 10 power 0.6. 3 into 10 power minus 1 into 10 power 0.6. That is nothing but 3 into 10 power minus 1 plus 0.6, how much? Minus 0.4.
4.
I can write this as 3 by 10 power 0.4. Yes or no? So given 10 power 0.08 is 1.2. 10 power 0.08 is 1.2. So using this, you can try to write down the value of 10 power 0.4. Try to write down the value 10 power 0.04 whole power 2 is equals to 1.2. It is 10 power 0.4. 0.08, it's not 0.08. 10 power 0.8 you take. That is 1.2. Because again we have to do 1 by 10. That will be again very high value. Okay, 10 power 0.8 you take. Because if I take 10 power 0.08, we have to again divide it, right? 0.08 into 10 by 10. That is 0.8 by 10. So that you will get in terms of 10 power minus 10 and all. So that's why you consider 10 power 0.8. 10 power 0.8 means 10 power 0.4 whole square. So 10 power 0.4 is nothing but root 1.2. So from there you can get this answer. Okay. Is that clear or not?
Yes, sir.
Yes.
Or you can simply go with the logarithm also. Instead of using them their value only, you can go with logarithm values. 10 power 0.4 you get, that is equal to some constant k. Apply logarithm. 0.4 into log 10 is equals to log k. Again, you have to find out like where that value is approaching closer to. Like 10 power 0.5 if you take, 10 power 0.5 if you take, that will be closer to what? 3.1. 10 power 0.5 is root 10. Yes or no? So you can just do with the closest value and then you will get the answer. Right, students? Try to solve this question. 1 gram of charcoal having surface area 3.01 into 10 power 2 meter square is mixed in 100 ml of 0.25 molar acetic acid solution. After some time, concentration of solution becomes 0.24 molar. What will be the surface area occupied by 1 molecule of acetic acid? So what they are trying to say, 1 gram of charcoal having surface area, this is 1 gram of charcoal having surface area given is mixed in 100 ml of 0.25 molar acetic acid. So there was solution, how much? 100 ml, concentration 0.25 molar. To this we have added 1 gram of charcoal. 100 ml of 0.25 molar acetic acid solution is there. To 100 ml of 0.25 molar acetic acid, we have added 1 gram of charcoal, which is having some surface area of 3.01 into 10 power 2 meter square. After addition, what happened? After some time, the concentration of solution becomes 0.24 molar. Slight change in concentration. 0.24 molar. What is the volume then? Volume. Like how much volume is there after the adsorption? Like we have to assume that whatever the 1 gram of charcoal we have added, that 1 gram of charcoal, on that 1 gram of charcoal some adsorption done. Because of this adsorption and because of addition of 1 gram of charcoal, whatever the change in volume is there, that you can neglect. If they have to given the final volume, if they have not given the final volume, you can neglect the change in volume happened. Okay, we can neglect the change in volume occurred due to adsorption. We can neglect the change in volume occurred due to adsorption or due to the addition of 1 gram of charcoal. So let us consider, if they have given the final volume, you have to take the final volume. If not given, then you can neglect. So 100 ml of 0.24 molar. What will be the surface area occupied by 1 molecule of acetic acid, that they were asking? So can I say 100 ml 0.25 molar to 100 ml 0.24 molar? How much is the number of moles of acetic acid that has been adsorbed, that you can calculate or not? So number of moles initially is nothing but concentration is equals to number of moles by volume. Number of moles is equals to concentration into volume. Volume will take in liter instead of ml, because directly you get number of moles. If you take in ml, you will get number of millimoles. Again, you have to convert. So number of moles initially is how much? 0.25 molar. Concentration into volume is how much? 1 by 10 liter. Because 100 ml is 1 by 10 liter. That is nothing but 0.025 molar. 0.025 mole. Number of moles. Number of moles finally is how much? 0.24 molar is the concentration into 1 by 10 liter. That will be 0.024 mole. So initially we have 0.025 mole of acetic acid. Based on concentration we have find out. Afterwards we have 0.024 mole. So this change happened. That means, can I say the number of moles adsorbed is initial number of moles minus final number of moles. Therefore, number of moles of CH3COH adsorbed is equals to number of moles initial minus number of moles final. So what is the initial number of moles? 0.025. What is the final number of moles? 0.024. What is the total number of moles adsorbed? 0.001 mole. That is 10 power minus 3 moles. So 10 power minus 3 mole of acetic acid. 0.001 means 10 power minus 3 mole of acetic acid has been adsorbed. 1 gram of charcoal have a surface area of 3.01 into 10 power 2. That means 10 power minus 3 moles. 10 power minus 3 moles. 1 mole means how many molecules? 1 mole means 6.02 into 10 power 23 molecules. 10 power minus 3 mole means 6.02 into 10 power 20 molecules. So these many molecules of acetic acid got adsorbed on how much surface area? These many molecules of acetic acid adsorbed on a 1 gram of charcoal whose surface area is 3.01 into 10 power 2. Therefore, I can say 6.02 into 10 power 20 CH3COH molecules adsorbed on how much surface area? occupied on a surface area of 3.01 into 10 power 2 meter square. Therefore, what they are asking, what will be the surface area occupied by one molecule of acetic acid? Therefore, one acetic acid molecule will be equivalent to 3.01 into 10 power 2 meter square divided by 6.02 into 10 power 20. So try to calculate 1 times 2 times 1 by 2 is 0.5. 5 into 10 power minus 1 into 10 power minus 18, that is 5 into 10 power minus 90 meter square. 5 into 10 power minus 90 meter square is the surface area occupied by 1 mole of acetic acid in this total process of adsorption. Is that clear, students? Is that clear to everyone or not?
Yes, sir.
Yes.
Yes, right. So based on the change in concentration, like with the same volume, we have find out number of moles got adsorbed. Like if the final volume is given, you can substitute the final volume, then you can calculate the relevant number of moles. This is the approximate value because we have neglected the volume change. Because of adsorption, because of addition of 1 gram of charcoal, there might be some volume change also. Yes or no? We have added 1 gram of charcoal, there will be some change in volume also that we have neglected here. So this is about the first point of surface chemistry, that is adsorption and all the phenomenon. Then you can go with the colloids. Colloids, what are colloids? Thomas Graham is the first scientist, studied the process of diffusion of dissolved substances through a parchment paper or an animal membrane and divide the substance into two classes. Like Graham was the first scientist who divided the substances into two classes. What are the substances he divided? Like crystalloids and colloids. Like how he classified, just based on the passage through the animal membrane or parchment paper. But later this classification has been wrong, and in reality we have to classify three types of substances. What are the three types? Colloids.
Crystal
Yeah,
colloid and suspense.
very good. Crystalloids, colloids, and suspension. How to categorize these three? Crystalloids, colloids, and suspension. All these three were actually classified based on the particle size. Like I have a particular water bottle here. In the water, I have added some NaCl molecules. Then what I am going to generate? I am going to generate a respective true solution. In the same water, instead of adding NaCl, if I add a protein molecule, then I can call it as a colloidal solution. In the same water, instead of adding a protein molecule, if I try to add some small sand particles, which can settle down at the bottom, then I can call it as a suspension particles. Yes or no? Thomas Graham, in 1861, he tried to study the process of diffusion of dissolved substances. But this classification soon proved to be wrong, since a crystalloid could behave as colloid under different condition. A crystalloid particle can also behave as a colloid particle. When a true solution can also behave as a colloid when the particles in the true solution coagulate. Yes or no? The coagulation of the particles in the true solution will make the true solution behave as a colloidal solution. So this classification was soon found to be wrong, and a new classification has been defined based on the size of solute particles. Crystalloids, colloids, and suspension. Crystalloids are also called as true solution. Colloids, colloidal solution, suspension. In the crystalloid, particle size is less than 1 nanometer. Colloids 1 nanometer to 1000 nanometer. Suspension greater than 1000 nanometer. So this was the particle size. Based on particle size, the classification has been done. Comparison of two solutions. True solution also called as crystalloid, colloid, and suspension. First one, you look at the particle size. Particle size less than 1 nanometer for crystalloid, 1 nanometer to 1000 nanometer for colloid, greater than 1000 nanometer for suspension. Visibility. Can you see the particle like crystalloid particle?
No, sir.
No, sir.
With any optical means you cannot see, but there are some other most advanced optical views like atomic force microscopy, where you can actually view the atoms. With the help of that, we can figure it out, but we cannot directly see them. So they are not visible with any of the optical means. Like with any microscope, you cannot see the crystalloid particle. May be visible with ultra microscope. For the colloidal particles can be visible with the ultra microscope. Suspended particles you can directly see with the human eye. Separation. With the filter paper, can you separate crystalloid?
No, sir.
No separation, because the particle size is very less. Through those pores, the particles are actually going. So with the filter paper, with the membrane also, you cannot do the separation. So separation can be done of crystalloid particles, not possible. With the filter paper, you can separate suspension. But with ultrafiltration, you can just to try to separate both colloid and suspension. But two solutions are not possible. Two solution with filter paper or with membrane, they are not possible to separate. Colloid is possible to separate with filter paper. Colloid is possible to separate with a ultrafilter paper, like ultrafiltration, but not with general filter paper. Suspension you can separate with both the filter paper as well as the ultrafilter paper. Right? Then look at the next properties like diffusion, settling, nature, Tyndall effect, and Brownian motion. Talk about diffusion. True solutions can diffuse greatly or not. Because of less particle size, they will be moving greatly. So diffusion greatly. Diffusion of colloid will also be there, but less when compared to true solution. So they diffuse slowly. Suspension, they settle down at the bottom. Suspension, what you can say? Particles settle down at the bottom due to gravity. Due to gravity also, the particles will settle down at the bottom. Nature of the solution, if you try to figure out true solution of crystalloid, if you try to figure out the nature, true solution or crystalloid, if you try to look at the nature, like what nature? Nature means, are they homogeneous or heterogeneous? True solution is homogeneous or heterogeneous?
Homogeneous.
Homogeneous. What about colloidal solution? True solution we have defined it. We have studied solutions. Solution is a homogeneous mixture of two or more components whose composition can be varied up to certain limits. If you go with the colloids and suspension, they are heterogeneous. So if you go with logics, so settling, true solution do not settle. Colloidal solution, they will not settle due to gravity, but it may settle under centrifuge. Centrifuge means there is a particular device where you can keep the colloidal solution and it will be rotating with very high RPM, like 1500 to 2000 RPM. Because of that very high rotations, the particles can settle down. Suspension can settle down due to gravity. Try to look at the nature. Nature is homogeneous for true solution. Colloid and suspension is heterogeneous. Tyndall effect and Brownian motion. Like colloidal solutions will show Tyndall effect and Brownian motion. True solution will not show Tyndall effect. Suspensions, they may or may not show. That depends upon the particle size again. Tyndall effect means scattering of light in all the directions by the respective particles. If the particle size in the colloidal range, then only you can have the scattering of light happening. You may ask a question, sir, why not a crystalloid particle do the scattering of light? Why? Like scattering of light, if you think of light, whatever the light we have, whatever the electromagnetic radiation we have taken, the wavelength of the electromagnetic radiation should interact with the colloidal particle or the whatever the dispersed particle we have. Like if the particle is very small in size, this much size, and the wavelength is somewhat like this for the source, will these two interact?
No,
This is
sir.
the electromagnetic radiation. This is the particle. Are they interacting at the first point? They are not interacting. So is there any change? So I have discussed about spectroscopy as well. Like in atomic structure, if you think of atomic spectra, emission spectra, spectroscopy is a branch of chemistry where we will be studying about the interaction of electromagnetic radiation with matter. Because of electromagnetic radiation interacting with matter, there are two changes. Changes can happen with the electromagnetic radiation, changes can also happen in the matter. Changes can happen in the electromagnetic radiation, changes can also happen in the matter. Right? Now, if you think logically, electromagnetic radiation, whatever you have considered, the wavelength of electromagnetic radiation is very much high than the diameter of the particle. Under that condition, there is no proper interaction. If the electromagnetic radiation do not interact properly with the matter, then you cannot have scattering of light happening. If the electromagnetic radiation can interact with the particle, like if the particle is somewhat a colloidal particle, which is in the range of 1 to 1000 nanometer, then the electromagnetic radiation can interact with the particle and then the scattering of light could happen. So colloidal particles can actually show the Tyndall effect, whereas the crystalloid particles as well as suspended particles, they will not have a tendency to show respect to Tyndall effect. And the details of Tyndall effect, like how the scattering of light will happen under what conditions, that we'll study in the respective properties. Is that clear?
Sir.
Yes, right. Right, very good. Types of colloidal solutions. A colloidal system is made up of two phases. Like a solution is made up of, solution means it contains two types of particles. One is solvent, other is solute. Similar to solvent, you have here dispersion medium. Similar to solute, you have here dispersed phase. What do you have? Dispersed phase. Similar, and whatever solution you are calling here, we can call this as colloidal solution. In the colloidal solution, we have dispersion medium and dispersed phase. Dispersed phase is the discontinuous phase. That means the particles are present somewhere at different points. Dispersion medium is like solvent, which is the continuous phase. Okay. The substance distributed as colloidal particles is called as dispersed phase or internal phase or discontinuous phase. The continuous phase in which the colloidal particles are dispersed, that is called as dispersion medium. Dispersion medium you can imagine like a solvent, and solute particles you can imagine, or you can take the analogy as a respect to solute. Example, if you try to consider milk, milk will have fat and water. Fat is the dispersed phase, water is the dispersion medium. Since in milk, what is the dispersion medium, we can't find out whether it has been diluted or not, because continuous phase is what? The continuous phase is water, dispersion medium is water. If I take milk and add water, I can't find out whether water has been added to milk or not. Yes or no? That is the advantage. Because we are adding a dispersed dispersion medium, which is a continuous phase. That is not an advantage, a disadvantage, because we can't find out whether the milk is pure or not. Classification of colloids. Physical state of dispersed phase and dispersion medium. Nature of interaction between dispersed phase and dispersion medium. Types of particles of the dispersed phase. Like based on these three types of, there are three types of classification. Like first classification means dispersed phase, dispersion medium we are trying to vary. Second type, we are trying to think of like changing the, looking at the interaction between dispersed phase and dispersion medium, like we call lyophilic and lyophobic. And the particles, as I have told you earlier also, multimolecular colloids, macromolecular colloids, and associated colloids, you can think of the last case. Let us go with the first classification. On the basis of physical states of dispersed phase and dispersion medium, we have 8 types. Interaction between dispersion medium and dispersed phase, we have 2 more types, lyophilic and lyophobic. Lyophilic sol, lyophobic sol. And type of dispersed phase particles, you can say multimolecular colloid, macromolecular colloid, and respective associated colloids. Is that clear or not?
Yes, sir.
right? Let us start with the classification of colloidal solutions on the basis of physical state of dispersed phase and dispersion medium. You can think of this classification: solid plus solid. You are getting what? Dispersed phase solid, dispersion medium also solid. Then what type of colloid you are getting? The first one is dispersed phase. Dispersed phase solid, solid, solid. Dispersion medium solid, liquid, gas. This is a dispersed phase. This is a dispersion medium. If the dispersed phase is solid and dispersion medium is solid, then you can have solid sol. Example, you can take ruby glass minerals. If the dispersed phase is solid, dispersion medium is liquid. Dispersion medium is now liquid. In that case, you can have sol. Type of colloid formed is going to be sol. Dispersed phase is solid, dispersion medium is gas. In that case, you can have aerosol, like dust, smoke. These are the examples. Examples you have to remember, students. Dispersed phase solid, dispersion medium liquid means you can have sol, like ink, paints. All these are examples. Dispersed phase liquid, dispersion medium solid. In that case, you will have gel, like jellies, boot polish. Dispersed phase, this is DP. Dispersed phase, this is DM. Dispersed phase liquid, dispersion medium is also liquid. Under that condition, you can have emulsions. Emulsion, you can have milk, butter, etc. Dispersed phase liquid, dispersion medium gas. Under that condition, you can again have liquid and gas means, like you can think of fog, mist, all those clouds. Aerosol, fog, clouds, mist, all that will be coming under this example. Again, dispersed phase gas, dispersion medium solid. Gas in solid will be a solid sol. Example, you can take a pumice stone, cake. Dispersed phase gas, dispersion medium is liquid. You can have foam, like dispersion medium is liquid, dispersed phase is gas. Under that condition, you can have whipped cream, soda water. All these are the examples. Why can't you have dispersed phase gas and dispersion medium gas?
Homogeneous mixture.
Yes, it will form a homogeneous mixture. If it is a homogeneous mixture, it is called as what?
True solution.
True solution. It is not a colloidal solution. So based on the difference in the physical state of the dispersed phase and a dispersion medium, we have tried to name different types of colloidal solutions, and examples of each category are given. So we have to take this very seriously, because questions will be directly asked, like pumice stone is an example of which type of sol. Foam is which type of sol. Fog is which type of sol. Like that, questions can be asked. Note, as I was saying, a colloidal dispersion of one gas in another is not possible, since the two gases would give a homogeneous mixture, but a colloidal solution is heterogeneous mixture. One gas, if you add to another gas, that will be forming a homogeneous mixture, but colloidal solution is heterogeneous mixture. So one gas in another gas, that is not a possibility we have. Then we have dispersion medium and nature of salt. Dispersion medium is water. Then we can call that as hydrozole or aquazole. Dispersion medium benzene, benzozole. Dispersion medium alcohol, alcohol. Like that, based on the dispersion medium, we can try to name different types of salts. If the dispersion medium has been changed from water to benzene, benzene to alcohol, the name of the salt can also be changed, like hydrozole, benzozole, alcohol, etc. If the dispersion medium has been changed, then the name of the salt can also be changed. All right. right? Classification based on interaction between dispersed phase and dispersion medium. Like lyophilic salts, lyophobic salts, you can have these examples. What are lyophilic? Lyophobic means what? Lyophilic means solvent loving. Lyophobic means solvent hating. That means the dispersion medium and dispersed phase, if they develop good interaction, if there is an affinity or attraction between the dispersed phase and dispersion medium, then we can say that is a lyophilic salt. If the dispersion medium and dispersed phase, if they do not have any affinity, then we can call that as a lyophobic salt. Then we can call that as a lyophobic salt. Lyophilic salts, colloidal solution in which dispersed phase has considerable colloidal solutions in which the dispersed phase has considerable affinity for the dispersion medium, they are said to be lyophilic salts. They are solvent loving. Example, you can take rubber, gum. These are all lyophilic salts. Dispersion medium, dispersed phase, they have attraction. Lyophobic means colloidal solutions in which dispersed phase has no affinity or attraction for the dispersion medium. They are said to be lyophobic salts. They are called as solvent hating. Example, you can take gold salt, arsenic sulfide. These are the examples of lyophobic salts. Is everything clear, students, so far?
Yes, sir.
Comparison of lyophilic salt and lyophobic salt, like different examples, how to compare between lyophobic and lyophobic. So lyophilic, how we can prepare them? So lyophilic means the dispersed phase and dispersion medium, they have the attraction with each other. So can I simply add dispersion medium with the dispersed phase? Like if I add dispersed phase to dispersion medium and shake it, I can actually directly prepare the lyophilic salt, because already whatever the two phases I'm adding, they have the attraction. Can I prepare the same? Can I prepare the lyophobic salt in the same way?
No, sir.
We cannot. Like if I want to prepare gold salt, can I add directly gold to water? If I directly add gold to water, it will not a sol. It will be a suspended. No sol is formed. So I cannot prepare lyophobic salt by simply adding dispersed phase and dispersion medium, because there was no attraction between the two phases. Like you can think of this, lyophilic salt can be easily prepared by shaking or warming the substance with solvent. But lyophilic can be easily prepared. Lyophobic salt, to prepare lyophobic salt, special methods are required. Cannot be prepared easily. Special methods are required. Stability, which is more stable, lyophilic and lyophobic? More stable due to attraction. Due to attraction. Due to repulsion. Due to repulsion between dispersed phase and dispersion medium. Reversibility, can you think of reversibility? Lyophilic salts are reversible. Reversible means what? Reversible means from the lyophilic salt, I can generate back dispersed phase and dispersion medium, whereas lyophobic salts are irreversible. I can write down here. Reversibility, lyophilic salts are reversible. That is, from the lyophilic salt, dispersed phase and dispersion medium can be obtained by evaporating and condensation, by subsequent evaporation and condensation. If you try to evaporate the respective lyophilic salt, like the dispersed phase particles you evaporate and condense it separately, dispersion medium particles you evaporate and condense separately. Like that, you can produce the dispersed phase and dispersion medium separately. You can separate them from the salt. That is why they are said to be reversible. But lyophobic can't be obtained in that manner. because they do not have any affinity. So that type of reversibility is not seen in lyophobic salts. Is that clear?
Yes, sir.
Yes, right. So let us proceed further. You try to compare this viscosity, surface tension, hydration or solvation. Viscosity, surface tension, hydration or solvation. Lyophilic sol, lyophobic sol. Viscosity is like friction. So due to more attraction between dispersion medium and dispersed phase, the ability to flow is higher or lower?
Lower.
The ability to flow is lower. That means viscosity is higher or lower?
Higher.
Higher.
Yes.
Higher. Okay, lyophilic means viscosity is much higher than that of solvent. Viscosity is nearly same as that of solvent. Why? Like surface tension and viscosity, if you try to think of for lyophobic sol, you think of a lyophobic sol like we have a particular water and you are preparing gold sol, let us say. Here we have dispersion medium, we have dispersed phase added. This dispersed phase is trying to separate out from dispersion medium to have minimum repulsions or not, because there was no affinity, there was repulsion between dispersed phase and dispersion medium. So dispersed phase will try to separate out, and dispersion medium means they mostly lie on the surface. So they try to not disturb any of the dispersion medium. So surface tension and viscosity of the lyophobic sol is almost same as that of just a pure dispersion medium. Like water you take and gold sol you take. Like water is one sol. Water is a pure dispersion medium. Water plus some dispersed phase. Lyophobic sol. The lyophobic sol, the viscosity and the surface tension of the lyophobic sol is almost same as that of viscosity and surface tension of pure water, because there was no interaction developed between water and the dispersed phase. But viscosity and surface tension in the lyophilic, what happened to surface tension in the lyophilic? Viscosity will be much higher, but what happened to surface tension? Surface tension is usually low. Why? Because whatever the particles which are present on the surface, they, once I add the dispersion, once I add the dispersed phase, the particles present on the surface will come and develop new attraction with the dispersed phase or not. So on the surface, whatever the particles are present earlier, they were forced to come inside to develop new attraction with the dispersed phase. Because of that, the surface tension has been decreased in the lyophilic. Understood this point or not?
Yes.
I repeat it again. Listen carefully. Lyophilic and lyophobic sol. Lyophobic sol, no proper interaction between dispersion medium and dispersed phase. Since there is no proper interaction, the viscosity and surface tension of lyophobic sol is almost same as that of pure medium. Lyophilic sol, if you try to consider, for lyophilic sol, viscosity is much higher. Viscosity is much higher than the dispersion medium, but surface tension is much lower. Why viscosity here is higher? Because the ability to flow has been decreased. Why the surface tension is decreased for the sol? Because whatever the particles, dispersion medium particles present on the surface, they are coming into now to develop new interaction with the dispersed phase. That is why surface tension has been decreased. Hydration or solvation, you can easily understand this. These are highly solvated because there was affinity. Lyophilic has affinity, so highly solvated. Lyophobic, no affinity, so these are less solvated as the particles have less affinity for the solvent. These are less solvated as the particles have less affinity for the solvent. Clear, right? Try to look at the few other properties. Charge, visibility, coagulation. Lyophilic salts, these particles have little charge or no charge. You can say lyophilic salts will have less charge. Lyophobic, more charge. The particles carry a characteristic charge, either positive or negative. Either a positive charge or a negative charge is present on the lyophobic salt. That is why the lyophobic salt particles, they are not going to be coagulated easily. What are the stabilizing factors for lyophobic salt? You try to think of stability of lyophobic. Is due to what? Why the lyophobic salt is stabilized? Lyophobic sol means what, students? We have some dispersion medium. In that dispersion medium, we have dispersed phase. When I can call this as a colloidal system? When the particle size lies between 1 to 1000 nanometer. Can I say if the dispersed phase particles are coming and forming an aggregate, the particle size is not 1 to 1000 nanometer if they form aggregate. So whatever the sol particle you have, that should be lying in the 1 to 1000 nanometer only. That means it should not come and form an aggregate. What stops the sol particles to form an aggregate?
Charge.
Charge. The hydrophobic or lyophobic sol particles will not come and form an aggregate. If they come and form an aggregate, they are no more a colloidal solution. They are forming suspension. Yes or no? If all the colloidal particles will come and aggregate, then it is no more a solution. It is no more a colloidal solution. It is a suspension. You may ask a question, sir, why will they form aggregate? Why can't they say separately in the colloidal particle range only without having any charge? If there is no charge, imagine the case of lyophobic sol. If there is no charge and the particles are there, you are asking a question, why can't they simply stay in the colloidal range? Why they are forming the aggregate? Because of intermolecular force of attraction. Because of, like, two molecules always attract or not? Two particles. Because of intermolecular force of attraction, they come closer and closer. If they have any charge, then only they'll repel and they will not form the suspended particle. If they have no charge, they will simply aggregate. It is no more a colloidal solution. So stability of lyophobic sol is due to charge. Due to charge of lyophobic sol. And we are saying the particles carry a characteristic charge, either positive charge or negative charge. Why? You may ask a question, sir, how do you say that lyophobic sol part have a charge? Due to adsorption of common ions on the surface of colloidal particles, charge will be developed. We'll discuss that. The reason for the charge formation we'll discuss in the upcoming slides. The charge is always there on the colloidal particle. Even though you consider lyophilic, there will be some little charge. There will be some little charge. Lyophobic, more charge. So charge is due to either preferential adsorption of ions or electron capture. In the metal salts, charge is due to electron capture. That is why most of the metal salts are negatively charged. In other type of salts, the charge can also be due to preferential adsorption. Stability of lyophobic sol, if you think of, due to charge of lyophobic sol, they are stable. Stability of lyophilic, you think of, one, due to charge. They also possess charge. Due to charge. The main reason is due to hydration. Lyophilic sol particle will be highly hydrated. The lyophilic sol particle, because of high hydration, like the sol particle is surrounded by very H2O. The sol particle is surrounded by very high number of H2O and also it possesses charge. So to coagulate a lyophilic sol particle, what I have to do? Think of this. If I want to coagulate a lyophilic sol particle, what are the things which I need to do? I have to remove the hydration, like water which are surrounding. The water has to be removed, as well as the charge also should be removed. If the water is removed and the charge is removed, then only the lyophilic sol particle is free from the hydration and charge, so that it can develop new intermolecular attraction with the other lyophilic particle, so that it can form an aggregate or coagulation can occur. Okay. So lyophobic sol, they were actually stabilized by charge. The reasons of charge are preferential adsorption or electron dispersion. Precipitated by high concentration of electrolyte, like coagulation of the lyophilic will happen only under high concentration of electrolyte. Coagulation will occur at a low concentration of electrolyte for lyophobic. Why high concentration of electrolyte I have to add? Not only electrolyte, along with electrolyte I have to add a suitable solvent also. Because you can imagine my wrist is a lyophilic particle, around it H2O is surrounded and it also has charge. And another lyophilic particle is here. These two should form an aggregate. If these two has to form an aggregate, first I have to remove all the water, like all the dispersion medium. How to remove the dispersion medium? I will now choose a solvent. I will add a solvent to the dispersion medium or to the colloid in such a way such that the solvent, whatever it is added, no, that will develop new interaction with the water. Water is actually surrounding this particular salt particle. If I add a solvent such that the solvent will develop new electrostatic force of attraction with the water, so water comes out of this attraction or not? Yes or no?
Sir.
Yes.
Water will come out of this attraction. So water have removed. That means whatever the hydration happened, that have removed. Now only charge is there. How I can remove the charge? I'll add an electrolyte. If I add an electrolyte, electrolyte has cations as well as anions. Let us say charge is positively charged. Colloidal particle has positive charge. So negative ions from the electrolyte come and utilize this positive charge. So ultimately charge I have to remove. To remove charge, electrolytes needs to be added. To remove charge, electrolytes needs to be added. To remove hydration, suitable solvent has to be added. Like that, I can actually do the coagulation of lyophilic. So comparatively, which is easy? Coagulation of lyophilic or lyophobic?
Lyophobic.
Lyophobic, because only charge I have to remove. Lyophilic, I have to remove charge and hydration. Right? Tyndall effect, lyophilic will have less scattering. Lyophobic will have more scattering. Migration in the presence of electric field, like they contain charge. That is why they will migrate, like may or may not migrate, because some lyophilic colloids will have very less charge. Because of that very less charge, their motion has been reduced. So they may or may not migrate, as they may or may not carry charge. Lyophobic will migrate towards anode or cathode, as these particles carry charge. If the colloidal particles are charged, they can be either positively charged or they can be negatively charged. So if the colloidal particle is positively charged, it will move towards negatively charged electrode, that is cathode. If the colloidal particle is negatively charged, it will move towards positively charged electrode, that is anode. General example you can take gelatin, starch, gum arabia, albumin, cellulose solution. And lyophobic can take transition metal salts like gold, silver, platinum, etc. Is that clear? Is everything clear so far?
Yes.
Right. Then comes the next classification, like after lyophobic, lyophilic and lyophobic, and after the type of physical state, classification based on the type of particles of the dispersed phase. First classification is multimolecular colloids. What are multimolecular colloids? Multimolecular colloids. Try to think of what are multimolecular colloids. Multimolecular colloids means there was a particular molecule which was lying in the crystalloid range only, but that molecule can actually form an aggregate which becomes a colloidal range particle. One molecule, if you take a particular molecule, it is in a crystalloid range only, but such molecules can form an aggregate and form a colloidal range. So they are said to be multimolecular colloids. Multimolecular colloids means formation by aggregation of a large number of atoms or smaller molecules of substance. Large number of atoms or smaller molecules, if they form an aggregate and they come into the colloidal range, then that is said to be multimolecular colloid. Example, you can take gold sol, sulfur, sulfur sol. These are the examples of your multimolecular colloid. So if you take one gold atom, it is not a sol. It is not a colloidal solution. Many gold atoms will come and form an aggregate such that they will lie in the colloidal range. So that is nothing but your multimolecular colloid. Multimolecular means simple molecules only which are in the crystalloid range. They will form an aggregate to form a colloidal range particle. Next one, macromolecular colloids. Macromolecular colloids means you can take proteins, any polymers. The polymers which are very large in size, they will automatically fall in the colloidal range, and a particular polymer in a suitable solvent, that is going to be your macromolecular colloid. And I'm saying suitable solvent. Why? because in the polymer, the long hydrocarbon chain may be different. So whatever solvent you are taking, so you take such a solvent such that the polymer and the solvent should develop electrostatic force of attraction. If they are not developing, then the sol cannot be easily prepared. Macromolecular colloids in suitable solvents, macromolecules form solutions in which the size of particles may be in the colloidal range. These colloids are quite stable and resemble true solutions in many respects. These colloids are quite stable and they resemble, like it's a true solution only, solute plus solvent. But just here the solute is in the very large size dispersion, dispersed phase, and the solvent is the dispersion medium. Okay, and the solution now we call this as a colloidal solution. Example, you can take synthetic rubber, man-made, starch. So all these will be forming the colloidal solutions. And then we have the third category. Third category is associated colloids or micelle formation. This we have explained earlier also. Like you can take soap solution, and cleansing action of soap can also be explained here. If you take a particular soap solution, in the soap we have a long hydrocarbon chain and we have a hydrophilic part as well. Long hydrocarbon chain is there which is hydrophobic, and a negative charge like polar part whatever is there, that is hydrophilic. What you can say in this aspect is substances which behave as normal electrolytes at low concentration but get associated at high concentration and behaves as colloidal solutions, those substances are said to be associated colloids or the micelles. What I have told you, whenever you try to add soap solution, like we have water here, whatever the stearate ion you are having, that will be arranged on the surface in such a way such that hydrophilic part will be lying on the surface, hydrophobic long chain will be lying away. When you try to add more soap, what happens? There are no surface points available such that whatever the extra soap you are adding, that cannot be occupied on surface, so it is forced to come into the solution. It will come into the solution in such a way such that it forms an aggregate. That aggregate is called as your micelle. So this micelle formation only occurs above a particular temperature as well as above a particular concentration. Above a particular concentration only this will occur. That concentration is said to be critical micelle concentration. Above a particular temperature only this micelle formation occurs. That temperature is said to be what temperature?
Critical micelle temperature.
Kraft temperature. Okay. Soaps and detergents. So you can think of associated colloids. Soaps and detergents are strong electrolytes and give ions when dissolved in water. C17H35CONa gives C17H35CO minus Na plus. So look at this sodium stearate. C17H35CO minus ion will be this much and Na plus ion will be there. So it will have what? Like hydrophilic tail of stearate ion and the hydrophobic tail of stearate ion and the hydrophilic head. This long hydrocarbon chain is hydrophobic tail. This polar part is hydrophilic head. Now we are adding this to water. How the micelle formation occurs? Look at this. Look at the animation. That is how the stearate ions are present. As the concentration is increased, what happens? They are actually forced to move into. As they move into, all the hydrophobic hydrocarbon chains will form a micelle. That is how the large aggregate is going to be formed, which is lying in the colloidal range. Understood this or not? The animation is clear now.
Yes.
Yes.
If the concentration is not very high, they will lie only on the surface. They won't come into the solution. Why they should come into the solution if the concentration is not high? They will try to. The hydrophobic already is lying away, no. So they have no tendency to come into a solution if the concentration is less than critical micelle concentration. The negative ions aggregate to form a micelle of colloidal size. In micelle formation, the long hydrocarbon chain or a tail which is insoluble in water. Why? Because the water is hydrophilic. Water has polar, hydrocarbon is non-polar. Polar or non-polar, they are not soluble. So long hydrocarbon chain which is insoluble in water is directed towards the center, while the soluble polar head is on the surface in contact with water. The charge on the micelle is responsible for stability of the system. The charge on the micelle that is actually responsible for the stability of the system. Because micelles are present in the colloidal range only, because they already have charge, they will not now form an aggregate. You may again ask a question, sir, why not micelle form an aggregate so that it becomes suspended particle? No, that is not happening. Why? Because they possess charge. Because of charge, one micelle particle and the other micelle particle repel. So aggregate formation is not going to happen. Critical micelle concentration. The concentration above which associated colloids or micelles are formed, that is said to be CMC. Below that concentration, no micelle formation occur because they lie simply on the surface. CMC of soap is 10 power minus 4 to 10 power minus 3 mole per liter. These colloids have both lyophobic and lyophilic part. The hydrocarbon chain is lyophobic. The polar part is lyophilic. Micelles may contain as many as 100 molecules or more. Like 100 molecules, 100 soap molecules can come and form a micelle. Okay, 100 soap molecules can come together and they can also lead to the formation of micelle. That is how micelles can be formed. Is that clear, students?
Yes, sir.
Yes or no? Craft temperature TK, as I have told you, the temperature above which micelles are formed. Below that temperature, micelle formation is not going to happen. Why? Because below that temperature, the molecular motion will be stopped. Because of, like, not stopped, it is reduced. Because of lesser molecular motion, the micelle formation is not going to be happening easily. So temperature above which micelles are formed, that is said to be Craft temperature. Necessary and sufficient conditions for micelle formation. What are the necessary conditions? In the same molecule, we should have a hydrophobic part and a hydrophilic part. That is a necessary condition. Compounds must have hydrophobic part, means long chain alkyl group. Compounds must have hydrophilic part. Hydrophilic means like the polar groups like CO minus. Some molecules have NR3 plus, like that. Okay, all these hydrophilic groups should also be there. Compounds must have hydrophobic part as well as hydrophilic part. Cleansing action of soaps. You can just look at the animation. Like what is the cleansing action of soap? This is the same thing we have discussed in the chemistry in everyday life. Whatever the particle you have, the particle or the dirt or the grease which has been stuck to the fabric, around that you will have the micelle formation. And when you try to wash that, along with the water, the micelle is taken out. The micelle actually holds the oil or grease, so that oil or grease is taken out from the fabric. Look at the animation now. So that is the respective dirt particle. On the dirt particle, we have micelle formation happened. And whenever you try to wash it, the negative charge developed attraction with water. So the dirt particle went away along with the water. Okay, this is how the cleansing action of soaps can be understood. The cleansing action of soap is due to the fact that soap molecules form micelle around the oil droplet. Around the oil droplet, the soap molecule form a micelle in such a way such that hydrophobic will be lying into, because hydrophobic, they don't want to develop attraction with water, and negative charge will be negative charge, or positive charge also can be there, because water has partial positive on hydrogen, partial negative on oxygen. So if the positive charge is there here instead of negative charge, that can also develop attraction with water, because partial negatively charged oxygen develop attraction, so that can also be taken out. Okay, hydrophobic part of stearate ions is in the oil droplet, and hydrophilic part projects out of the grease droplets like bristles. Hydrophilic part will be projecting out like a bristle, and those all develop new attraction with water whenever you try to wash with water. Right? Oil and grease can be absorbed into hydrophobic centers of soap micelle and washed away. Thus, soaps helps in emulsification and washing away of oils and fats. That is how you can have the cleansing action of soap occurring. That is how you can actually have the cleansing action of soap. Just a minute, students, I'll be back. Right, students? So that is how you can actually understand the cleansing action of soaps. Same thing, negatively charged sheath around the globules prevent them from coming together and thus forming an aggregates. Whatever the negative charge is there, that will have electronic repulsions. Because of the electronic repulsions, they will never form aggregate. So that is also a way to understand this particular cleansing action of soaps. The next point is preparation of colloids. After we have seen the classification so far, what types of classification we have seen? Classifications based on physical states of the dispersed phase and dispersion medium. 8 types we have seen. Classification based on attraction between dispersed phase and dispersion medium, lyophilic, lyophobic, different categories, examples. Classification based on type of dispersed phase particle, multimolecular, macromolecular, and associated colloids, and cleansing action of soaps. Now, the next point is methods of preparation. Lyophilic salts may be prepared by simply warming the colloid with a liquid dispersion medium. Lyophilic salts may be prepared by simply warming the solid with a liquid dispersion medium. How you can understand this? Because there is an attraction between the colloidal particle, like a dispersion medium and dispersed phase, we can say by simply adding the dispersion medium to dispersed phase and shaking it well, you can actually prepare the lyophilic salt. But that is not applicable for the lyophobic salts. To prepare lyophobic salts, special methods are there. Example, you can take starch in water. Lyophilic salt, you can add directly starch to water, you will generate a lyophilic salt. On the other hand, lyophobic salts have to be prepared by special methods. Why? Because there is no affinity between dispersed phase and dispersion medium. These methods fall into following categories. First one is electrodispersion or Bredik's arc method. First one is electrodispersion or Briggs arc method. What happens in this particular method? Whatever the metal we have, that is subjected to very high temperature because of the electric spark. Like an electric arc has been stuck between the metal electrodes. Because of the extremely high temperature produced, the metal will be vaporized. The vaporized metal will be going and the total system is actually taken in the ice bath. As the vaporized metal goes to the atmosphere, like again as the temperature is low, it will come back to the solution. It will come back and fall to solution in the dispersed phase particle. Like what happens? The vaporization occurs and the condensation again occurs. So you can understand the same scenarios. This method is suitable for the preparation of colloidal solutions of metals like gold, silver, and platinum. This is a system. We have an ice bath and we have a beaker where we have a particular dispersion medium and we have placed a metal and we'll now subject that to electrical arc. Extremely high temperature generated is now going to vaporize the metal and then the vaporized metal will come back and condense to form a colloidal solution. So that is how the electric arc has been given and the metal has been formed, the vapor of the metal that will again condense back to form the respective colloidal solution. Is the animation clear or not?
Yes, sir.
Yes, no? This process involves dispersion as well as condensation. Like vaporization occurred, an arc is stuck between the metal electrodes under the surface of water containing some stabilizing agents such as traces of KOH. We are actually giving the external electrical energy. Because of that external electrical energy only, the metal electrodes, whatever they are there, they are going into the vapor phase. As they are going into the vapor phase, again the temperature, because of ice bath, the temperature above is low, that vapor again condenses back to form the respective this colloidal solution. The water is cooled by immersing the container in ice bath. The intense heat of the intense heat of the arc vaporizes some of the metal, which condenses under cold water, to form the colloidal solution. That is the first method, Briggs arc method. Second method is peptization. Peptization is the process of converting a freshly prepared precipitate into colloidal solution by shaking it with a dispersion medium in the presence of small amount of electrolyte. Whatever the precipitate we have, no, the process of converting the precipitate, into freshly prepared into colloidal solution by shaking it with a dispersion medium. How we can do that? How can we do that? Like if you go with the details, we have a particular solution. In that particular solution, we have dispersion medium, and precipitate is formed. This precipitate, the process of converting a freshly prepared precipitate into colloidal solution by shaking it with a dispersion medium in the presence of small amount of electrolyte. The electrolyte, whatever it is added now, that is going to develop charge on the precipitate. Because it develops charge, the precipitate will be splitting up into small colloidal particles. And that electrolyte add is said to be peptizing agent. Like AgNO3, Ki, if you try to add, AgNO3 and Ki, if you try to add, AgI is going to be developed. And you have added the electrolyte. You can see AgNO3 plus Ki. If you try to add, AgI is formed. Along with AgI, KNO3 is formed. AgI is the precipitate. To this precipitate, you have added some electrolyte. That electrolyte developed charge on the precipitate so that the precipitate is now broken down into the colloidal particle. Understand this sequence again. See, look at the animation. AgI and AgNO3 and Ki you are adding. AgNO3, Ki, if you try to add, you will form AgI, which was a precipitate. Now we have added an electrolyte. That electrolyte is going to develop charge on this particular precipitate molecules. As it develops charge, it will break down the precipitate into smaller colloidal size particles. Yes or no? The charge has been developed by preferential adsorption. Like you may ask a question, sir, how the charge is developed. We'll discuss that. The charge, how the charge is developed. If I try to add AgNO3 to Ki, if Ki is dispersion medium, if AgNO3 is dispersion medium, what type of charged sol is formed, that we'll discuss in the next class. Fine, students. Thank you all, everyone. Bye.
Thank you.
Thank you, sir.
And we all have a session tomorrow. Kindly attend it. So I'll be discussing solid state. So we'll be discussing solid state. We have discussed some part of the solid state in the last session, Saturday session. We'll cover it up. Okay, thank you.
Thank you, sir.
Thank you, sir.